Hi folks, welcome to the third video of this end-to-end NLP series. In the last video, we have gone through the theory behind byte pair encoding algorithm. In this video, we are going to look at a step-by-step implementation of byte pair encoding tokenization algorithm in Python. If you have not watched the theory part yet, I would highly suggest you to check that one first and then get back here because we will be referring to that video a lot of times. So anyway, if you know already the theory part, we are good to go. So let's get right into it. We have already seen that tokenization method first creates the vocabulary, and then based on the tokenization based on the prepared vocabulary, it tokenizes the unseen data. So we shall look into the vocabulary preparation first and then come to the tokenized part. Now this fit method is actually takes in a corpus and then creates a vocabulary using BPE algorithm. We shall split the fit function into two separate parts. The first part will be responsible for initializing the vocabulary and also other helpful artifacts. In part 2, we shall look at how to populate the vocabulary. As you know, you already know how to populate the vocabulary from the theory, but we will see how to implement that in code. So let's jump into the part 1 first. So this is the part 1 of fit method, and we will have the same corpus that we have used in the theory part as well, the simple crazy corpus. And the very first thing that we are going to do is normalization. So as we are doing text normalization, we are basically removing all the replacing all the non-alphanumeric characters, meaning whichever are punctuation marks and also not falling in this A to Z or 0 to 9 spectrum. We are replacing those using a space, and also we are turning the capital letters into small letters. So this is just the normalization part. After normalization, we are going to split that corpus into separate words, and this while splitting into separate words, we will also ensure to include an underscore in the end at the end of the word, because this will signify the end of each word in our algorithm. Next, we will be initializing 4 things. So first, BP vocab. We all know what is that. It is the one which will contain all the derived subword tokens. This will include the unique letters in the corpus as well. BP letters. This will only include the unique letters of the corpus. This is just to keep the initial letters separately. That's it. This will help in future when we are going to tokenize unseen data, because we will be seeing if there are some unknown letters that are not present in the corpus. BP merges. BP merges will contain the merge rules that we will be learning in the part 2 of fit method. So we are not reaching there yet. Corpus vocab counts. Corpus vocab counts will contain tuple of characters in the keys and frequencies of them in the values. With the dry run of this code, we will be easily understanding what is happening here. Maybe explaining in words a bit ambiguous, may seem a bit ambiguous to you, but once we go here and update our corpus vocab counts, you will see exactly what is happening. So let's go into the loop now. So what we are doing, we are looping over our corpus, and we are updating 3 things: BP vocab, BP letters, and corpus vocab counts. This is for the initialization part. BP merges will not be initialized because this will be populated as we learn the merges statistically. Now, how BP vocab and BP letters update? Easy. These are sets, so it will be updated by the letters of the current word. Next, what we'll do, instead of splitting the word into a tuple of characters in it, we will keep a space in between the characters. So initially crazy was like this, and now it is just space. I mean, there are spaces in between the letters. The main motive of doing this in future, if we need to combine two characters, we can easily delete the space in between, and if we want to get the individual characters, we can split based on space. So this will make our life a bit easier, and we then need to add it to our corpus vocab counts. So in the corpus vocab counts, we are just maintaining that this crazy word, how many times we have seen the crazy word in our corpus. So right now we have seen only one time, so it is updated with just a value of 1. Now if we go to the next word, this will be crazy again, and the crazy part is BP vocab and BP latest will not be updated, it will be the same. Not actually crazy, it's quite predictable, right? Because these are sets, so it is already, the letters are already there, so it will not include anything more. But in case of corpus vocab counts, this will be changed to 2 now. So initially it was 1, now it is changed to 2. Why? Because right till now we have seen crazy 2 times. So if we run the loop entirely now, we will have these complete initializations of BP vocab, BP letters, and corpus vocab counts. As you can see that crazy, crane, dance, pan, game all have the numbers, all have the frequency counts in the which basically signifies that how many times they have occurred in the corpus. All good. Now these initialization of BP vocab is actually almost complete, but it's not fully complete. Can you guess why? I think you have already guessed it, because we have used only unique letters from the corpus, so we need to handle the out of vocabulary letter, and that is exactly why next we are going to add an unknown token in the BP vocab to handle the unknown letters or unseen letters. Now with that we have come to an end of part 1. Let's jump into part 2 now. So now we are going to populate our vocabulary. So let's start with the first iteration. So we are going to initialize a bigram counts variable. What is this bigram counts? We will see. But one thing is, we will be using all these things, so it's better to keep these on the screen. So corpus vocab counts is currently at this position, VP vocab is currently at this position, PP merges is empty. So as we go forward, we will be seeing that which corresponding pairs, which consecutive pairs, pair of letters in the word has occurred most frequently, and which consecutive letter can be combined together and included in the BPA vocab. So we will see that in the loop. So now if we go forward, we will see that we are looping over corpus vocab counts. Now corpus vocab counts has got different keys, unique words from the corpus. So first we have crazy. Now in here, what we are doing, we are taking subsequent words, subsequent letter pairs. So we are just adding 1 colon to get a shift, and then using zip function to create these tuples. So CR, RA, AZ, so all consecutive letter pairs, right? Now from these bigrams, we will fill up these bigram counts. Can you guess what will be filled up here? I think this time also you have guessed it correctly. We are going to take the frequency of those, right? Frequency of these tuples in our corpus, and we will update that frequency in the bigram counts. So if we go forward, we see that we are now iterating over bigrams, and the first bigram is CR, and as CR has occurred in the crazy word, and crazy word has occurred 3 times in our corpus, so ultimately CR consecutively has appeared we have seen CR appear 3 times in the corpus so far. So we have not seen the other words yet. It may be more. It may be that CR has appeared more than 3 times in the corpus. In other, CR can be present in other words as well. But for now, for this moment, till this moment, we have seen CR only 3 times. Now, as we go forward, we are going to the second bigram, and as you can guess that for all the bigrams here, by the bigram meaning I am referring to this one consecutive pair of characters. I am referring to one consecutive pair of characters as bigram. Now, as you can guess that all of these bigrams will have frequency of 3 for now, because we have just seen one word, right? So if we go forward, we will see that all of them has initialized with 3. Now, if we move to the second word, now we are moving to the second word and we have come to crane. And if we go into it now, we will see that crane has been split into these consecutive character pairs, and CR is now having a frequency of 5. Initially it was 3, so now 2 more has added, because CR was present in crazy, which had a frequency of 3. Now CR is present in crane 2, which has a frequency of 2. So CR has appeared 2 times again, so 5 in total. So that's what we are doing. We are calling the frequency of the word and adding to the previous frequency. So this is the past frequency and this is the current frequency of the consecutive pair. Hope you are getting it, right? So after you are done with this, if we loop it through the entire we complete the loop, then we will get the entire bigram counts dictionary, and this is how it will look. From here now we need to identify which one has got the highest frequency, and as we can see, AN has the highest frequency of 6. What is the next part? The next part is combining AN together, right? Because AN has appeared most frequently, so it makes sense to make a token out of it. So combining AN together and updating it in corpus vocab, as well as BPE vocab, included in BPE vocab and included in BPE merges as well. So we are going to do that exactly. So as you can see, now we are iterating over old keys. What is this old keys? Old keys is basically these keys of corpus vocab counts. So these are old keys. So as we are iterating through old keys, we will we will find AN in one old key, we will replace that AN with the combined AN character. As we said in the part 1, that if we want to combine 2 characters together, we will just delete the space in between, and that is exactly what we are going to do. So this is where we are getting an AN. So we have come to crane, and there was an AN before, and now this AN we are going to combine together and make it like this. And we are going to do that for every word which has AN here. So dance, pen, and this is how it will look after the loop has finished. Next, we are going to include AN in BPE vocab as well. So BPE vocab, AN is included. BPE merges, we are going to initialize a new entry, AN merge rule, with the highest frequency. This highest frequency, we are just keeping it for information. There is no practical use of it in our algorithm, but this tuple will be useful. So let's go to the second iteration now. We have completed only one iteration till now. So in the second iteration, we will do the same thing, and you may think that we will be getting the same thing, and in the first word we will be getting the same thing as well. You are right, because crazy, there were no merges in the word crazy, so it will be the same. But in case of the next word, it will be a bit different. You see, in case of crane, initially it was A and N, so A, N, both characters were separate, but now A, N is combined and acting as a single character. So when we are splitting with respect to space, we are actually taking we are not actually splitting an because there is no space in between an, so an is going to be treated as a single character. So in a pair, now r and an will be a consecutive pair, and we will have these two new entries, ran2 ane2. And in this way, if we increase the number of iteration of this BP algorithm, then the number of then the length of these consecutive pairs will be longer each time. Okay, and the more we do, the more we iterate through it, the more we will include the frequent words together. Okay, so if we complete it now, this is the bigram counts. This is how it looks, and you can see CR has got the highest frequency, and the next part, this will be included in uh, vocab counts. So vocab counts CR is combined now. Wherever CR is there, we have combined them together and made a single character out of it, and we have included in BP vocab and BP merges as well. For example, we are going to stick with 2 iteration, but this is very few. So what we need to do in case of a bigger corpus, as we will see with the Wikipedia data, we need to iterate at least like 500,000 times. Okay, now let's go and see how to use this vocab that we have prepared in the fit method to tokenize the unseen data. So this is the tokenization function. So we are going to take a test data which is sand. So we'll just take one word and see how the algorithm is performing. So the initial phase is basically the same. We are going to normalize sand, and then we are going to split it into letters and add a small underscore at the end to signify the end of the word. Now what we are going to do, we are going to iterate over BP merges, the BP merges that we have got from fit method. So this was our BP merges, if you remember, right? Now the first merge rule that we encountered was AN. So now we need to find AN in our splits and combine them together, and that is exactly what we are going to do. We're going to start iterating over this list, over these letters, and we are going to keep a pointer. So this I will be pointing the current position of us. So initially it is 0. Now it is going forward and going up to the second last element, because we will be taking pairs. So if it goes to the last element, there will be no next element. So there will be an error. So we'll see that it will come intuitionally. So as I is staying here right at the 0 position, we are going to take the I plus 1th character as well and create a pair, consecutive pair. So S and A, and we are going to see whether it is matching with the current merge rule or not. The current merge rule being AN, it is not matching with SA. So what we will do, we will move forward and we will push the I to the right. So I was initially here, now I is 1. Now as I is 1, we are going to do the same thing, and we are going to take the next letter, I plus 1th letter, and create a consecutive pair, and we will check whether now it is the same with the current merge rule, and it is same, right? It is same, so we are going to do a merge on it. So voila, it's merged now. Now we have this merge character, the character is changed, and possibly, it may be possible that now the consecutive character is going to match again. So that's why we are not updating our I, we are not pushing our I in this case. We are keeping our I here. Only when we are not getting a match, like now AN and D is the new consecutive pair and it is not matching with AN, so then only we will push I towards the right. And now I has reached the final location, as D underscore is the pair now, and it is not matching, and I can't go further because if I is here, as I said, it will not get any element here. So our loop will go through the list again one more time, because there is one more merge rule. So if we quickly scan through the list, we can see there is no match, so we are done. And last one thing is, in this tokenized version we need to handle the out of vocabulary letters. So we will scan through our BPE letters and see which characters are not present in these BPE letters, which single length characters. So S is not there in our BPE letters, so we will replace it with an unknown token. And this is our final tokenized form of sand. Hopefully I made this clear to you. To see how it performs in the real data, we will see, and we will see how it works for the Wikipedia corpus. So this is where we are going to use Wikipedia API for Wikipedia data collection, and then we will see how our byte pair encoding algorithm is performing over it. And this Wikipedia API, by the way, is open source, so you can use it for free. All you need to do is give your name and some index value, and then your email ID in bracket. You need to follow this syntax, and then you need to give the language of the page that you want to fetch. And after that, you have initialized your Wikipedia API, and from there you can just call wiki.page and the name of the page you want to access. So I want to access the natural language processing page, so I'm just giving the name, replacing the space with underscore, and it is giving me the page link, HTML page link. Now from there I can just fetch the text attribute, which have all the full textual data in the article, and it will dump that in a string format in corpus, right? So now if we take the length of the corpus, we can see that there are 32,652 characters in total. So it's not too large, not too small, kind of in the middle ground. I like it. So let's see and initialize our BPE class. So what I have done here is I have written a class for BPE, and I have kept a fit function. Whatever fit function we have seen there, I have just kept that here, and a tokenize function as well. So we need to initialize BPE first. After that we can do a bpe.fit corpus number of iteration. I have kept 1000. As I said, the more number of iteration you keep, the more frequent subwords you are going to catch into your vocabulary. So we have kept 1000 in number of iterations, and let's run it. So as it is running, the vocabulary will be built in the backend, and it will be saved as an attribute of this BP class. And now it is done, so we can just run bpe.bpe merges to see what are the merge rules we have learned. So as you can see, it starts declining. The frequency, the average frequencies that we are seeing in the front, it is quite large, but as we go down, go in more depth, we can see the frequencies are dropping. So E underscore has a frequency of 893, meaning that in our corpus there are a lot of words ending with E, ending with S, having IN together. So all these things, right? Now if we use a test data to test how it is tokenizing, I'm going to take a test sentence, and the sentence will be very similar to NLP, so close to NLP domain. It will be talking about NLP domain. A lot of machine learning algos are used in NLP, but transformers are the best right now. I have kept this sentence intentionally NLP focused because I wanted to see how it is recognizing the data. So if we run it now, as you can see that the articles and the prepositions, vowels, all these things, are easily captured together as a whole token. So a, in, but all these are captured as an entire token. All these things, uh, in some cases that it can't identify fully, like you see algos, it has not figured out the entire word, but it has kept some subword. So alg it has kept, ace underscore it has kept, so it knows something about the word. It is not like it is completely in the dark. So that's the power of subword tokenization, and that's how it works. Hopefully the code also you can use, the code you understood, and the code you can use in your own personal projects. In the next episode, we will be looking at word piece algorithm, another subword tokenizer, and it is very similar to BPE. If you have understood BPE, word piece will be a piece of cake. So yeah, that's it for today, guys. Thanks for watching. Keep learning. Bye bye. Good night.